Okay, students, welcome back. In this video, we're going to talk about objects in free fall. This is the last section in this chapter. And so if you're watching the video, please be following along in your guided notes and fill out the guided notes as we go through these slides. Okay, so objects in free fall. I want you to write down the definition for free fall. So it says here that free fall is the state of motion that is encountered by an object that is being acted upon only by the force of gravity. Okay. So free fall is a state of motion that is encountered by an object that's being acted upon only by the force of gravity. So if it's got a motor on it, is it in free fall? No. It's something that's only being acted upon by gravity. Its motion can only be traced back to gravity. That's it. So that is an object in free fall. So this pen, if I let it go, is it going to be in free fall? Yes. It's only being acted upon by gravity. Gravity is the only thing that is making it move. It says responsible for that pen's motion.
So if you throw it down, does that still count as free fall? Or no?
Yes, yeah, it would. It would. Because it's still only falling because of gravity, right? Good question. So if you throw something down, still is in free fall. Okay, good question. All right, there's two important motion characteristics that are true of free-falling objects. Number one, for our calculations, free-falling objects do not encounter air resistance. Now that's for our calculations, but in reality, would an object experience air resistance? Yes. But for our calculations, free-falling objects do not encounter air resistance. But of course they will in reality. Okay? Now why don't we account for air resistance in our calculations? Because it gets way too complex. It depends on the shape of the object, its angle that it flies through the air, and a lot of calculations that we just can't do at this point in time. Okay, and number two, all free-falling objects on Earth accelerate downward at a rate of 9.8 meters per second squared. So acceleration due to gravity on Earth is 9.8 meters per second squared. Another important point, gravity always pulls things in which direction?
Towards the center.
Towards the center of the Earth. So doesn't gravity always pull things down?
Yes.
So is this going to be a positive or a negative 9.8?
Negative.
On our equations, you're going to have to remember to put a negative 9.8 meters per second squared because it's going down. And remember, down in physics is negative. Okay, now would this be true on the moon? Would gravity accelerate things at a negative 9.8 meters per second squared on the moon? No. What about on Mars? So if you're a NASA scientist, are you going to use negative 9.8 meters per second squared to try to land the Mars rover? No. They can figure out what it is on Mars. Yeah?
So since we're being constantly pulled by gravity, does that mean we're constantly in free fall? No.
Well, no, because we've got the ground that's stopping that motion, right?
Yeah.
But if there was no ground, then yes. We'll talk about stuff like that in the next chapter. Those are good questions, though. Okay, free fall. In your book, before I go to the next slide, in your book it says draw a ticker tape diagram for an object in free fall. Now, guys, we did ticker tape diagrams last chapter and we did them horizontally.
Yes.
Remember the dots? Okay? What I want you to do in your notes is draw a ticker tape diagram for an object in free fall, but I want you, because the motion is vertical, to draw it like its motion vertically. So draw the dots in there for an object that would be in free fall. And let's see if you guys can get it right. If you're watching the video, hit pause and do that, and then we'll see if you get it right. Okay, an object in free fall. Is it constant velocity or is it accelerating?
Accelerating.
It's accelerating. So how many of your ticker tape diagrams look like this? Okay. At the beginning, they should be very close together. But what's happening as it falls?
Gets farther apart.
Gets farther apart. Why?
No, why? It's falling.
Because it's falling. And so each time interval, it increases distance because it's accelerating downward. Okay. So here's an important point. Oh, Chase.
What about when it reaches terminal velocity?
Good. Good question. What if it reaches terminal velocity? Do you guys know what terminal velocity is?
The max speed it can reach.
The max speed it can reach because what happens?
It reaches the equilibrium of
Between gravity and what?
air resistance.
Air resistance. But in our calculations, are we considering air resistance? No. But in reality, would objects experience terminal velocity?
Yes.
Yes. But in our calculations, Chase, we're just going to ignore air resistance. Again, because the calculations would be too complex.
The graph would be constantly back.
Okay, good question. So there is no terminal velocity with these problems. All right, here's another important point I wanted to point out, guys. When he releases it,
Oh, really?
what's velocity initial here when he releases it? Whenever you drop something, it's going how fast?
Oh.
Okay, always keep that in mind. When you release an object, it doesn't have to start from zero, right? Yeah. And so your initial velocity is going to be zero. Now, the final velocity down here, it's going to be much faster, but we're going to figure out how to calculate that. How fast is the object going right before it hits the ground? Okay. Some other questions that we're going to have. How long did this take? So time. We're going to be able to answer questions like that. So stay with us. Here we go. Gravity will accelerate an object in free fall with the rate of 9.8 meters per second squared towards Earth, towards the center of the Earth. Gravity always pulls toward the center of mass. Acceleration of gravity is given by the symbol g. So whenever you see this little lowercase g symbol, that means acceleration due to gravity. What does g equal? Well, g equals 9.8 meters per second squared downward, or this is how we're going to most likely see it in our calculations, negative 9.8 meters per second squared. Again, negative because it's going down. Okay, before we go to a practice problem, acceleration due to gravity can either be given the symbol lowercase g, or sometimes you just see it as a. What does a mean, guys? Acceleration. Isn't acceleration due to gravity acceleration?
Yes.
Yes. And so you might see it as a, but again it's just negative 9.8 meters per second squared. Or you might see it as lowercase g. Again, they mean the same thing. So if you want to make a little note of that, for objects in free fall, they're going to accelerate and have the same value. Okay, I've got a number of practice problems that we're going to go through. Practice problem number 18. It says, if acceleration due to gravity is 9.8 meters per second squared, what would the velocity of a rock be at 1, 2, 3, and 4 seconds after it was dropped off a cliff? For these questions, guys, I promise you it will help you if you draw a picture. I'm not very good at drawing. Stick figures work great. He's on a cliff. Okay? He's going to release, what is it that he's dropping? A rock? Okay, a rock. At this point, there's the rock. It wants to know its acceleration due to gravity at these different time intervals. Let's start with actually time is 0. So time equals 0 is when he releases it. 1 second, it's going to be, I don't know, maybe about right here. So t is equal to 1 second. At 2 seconds, it's going to be a little bit farther apart. So t is equal to 2 seconds. t is equal to 3 seconds. And finally down here, t is equal to 4 seconds. Okay. What is his, what would the velocity, we want the velocity of the rock. What is the velocity of the rock at 1 second? Here's a hint. It's accelerating at 9.8 meters per second squared.
So divided by that?
So what is it going at 1 second? 9.8 meters per second. But it's going down, so what should we do? Put a negative sign in there. Okay. So at 1 second, it's going negative 9.8. What's it going at 2 seconds? How do we figure that out? What's 9.8 times 2? Negative 19.6 meters per second. Again, it's going back to what exactly does acceleration mean? It means it's going at 9.8 meters per second faster every second. So what would it be going at 3 seconds? 9.8 times 3. So that's a negative 29.4 meters per second. Okay. How would we figure it out for 4 seconds? 9.8 times 4. Are you guys getting negative 39.2 meters per second? Okay, I hope that we have a sense of what acceleration actually is. Every second, it's getting 9.8 meters per second faster. So again, it's 9.8 faster. And again, it would be 9.8 meters per second faster than it was before. Does that make sense what acceleration is? That's why it's meters per second squared. Because every second, it goes that much faster. Okay. So did we get these? Well, of course at time 0, he hasn't let it go yet, so his velocity is 0. 1 second is 9.8, 19.6, 29.4, and 39.2. Did we get those? That you guys got? Okay. Those were the answers. And you can keep going. Time equals 5 seconds or even farther. So, okay. Free fall equations. We are going to use these equations a lot coming up. So take a second. I want you to jot down these 3 equations, 1, 2, and 3, in your notes. Write them down, and then we'll talk about them. Okay, now let's take a second and explain what each one of these variables mean. Let me see if I've got it on the slide here. Okay, let's look at equation number 1. What does V mean, guys? Velocity. What do you think this little subscript F means? Final velocity. So velocity with a little f by it means final velocity. Okay. What does V mean again? Velocity. What do you think the little I means? Initial. Okay, I want you to make these notes in your book somewhere, on the margins, the top, the bottom, the side, somewhere. You should know what each one of these things mean. What does A mean? Acceleration. And in free fall problems, it's going to equal something. What does it equal? Negative 9.8 meters per second squared. For objects in free fall, it's always going to be that. Okay, make note of that. T, what does T mean? Time. In what units do we measure time in? Seconds. So time is measured in seconds. Okay, so that's equation number 1. Velocity final is equal to velocity initial plus acceleration times time. Let's go to equation number 2 now. We see another variable, D. What does D mean, do you think?
Distance.
Close. displacement. Let's call it displacement. And what do you think d sub f means?
Displacement.
Yeah. So let's put displacement final. Okay. Okay, then we see d sub I. What does that mean? Displacement initial. Okay. What its displacement is when the problem starts. Okay, v sub I again. What was that one, guys? Velocity initial. Oh, t sub f. What does that mean? Time final. Plus 1/2. What is a? Acceleration. So that's going to be a negative 9.8 always for free fall objects. And t sub f. What is that? Time final. But what do we got to do to it? Square it. Okay. So there's no new variables after that. Let's go to number 3 and make sure we understand everything here. What is v sub f? Velocity final. What do we got to do to it? Square it. Is equal to, what's v sub I? Velocity initial. And what do we got to do to it? Square it. Plus 2a. What's a? Acceleration. And what is it equal to in these problems? Negative 9.8 meters per second squared. What's d sub f? Displacement final. So that's the object's displacement when the problem is over. Minus d sub I. What is that? Displacement initial. So when the problem begins, it's displacement. Okay, I've got 4 practice problems coming up. Stay with me. We're going to use those equations, and let's see if we can answer these questions. Practice problem number 19. It says Luke drops a pile of roof shingles from the top of a roof located 8.52 meters above the ground. Determine the time required for the shingles to reach the ground. Choose one of the following equations to help you solve this problem. Okay, always, always, always. What do you do? What's your first step? Draw a picture. Let's draw a picture. Okay, he's on this roof. I'm not very good at drawing pictures either. Let's just draw a flat roof. He's up here. Okay, he's dropping these shingles. Okay, the shingles are going to come down and fall and hit the ground. We want to know how much time it takes for them, right, Sam? Okay, pay attention. I promise you guys are going to have to get used to doing this stuff. Okay, and it gave us some information. It says the roof is located 8.52 meters above the ground. That's important. Okay, so underline that. Now, before we even pick an equation, we're going to pick one of these 3. But before we do, let's list all the variables that we know. Okay, let's start with the easy ones. What's velocity initial of these shingles? Right when he drops it, good. It's 0 meters per second. Now, do we have velocity final? No. So I'm going to put a little question mark there. What's time initial when he drops it? 0 seconds. Okay. What's time final? We don't know. That's really what we need to find out. So I'm going to put a box around it. Okay. What's displacement initial? The point at which he releases it, the displacement is what?
0.
I'm going to call it 0. 0 meters. Now, what's the displacement final?
8.52 meters.
Okay, it's 8.52 meters, but
Negative.
did they end up below where he released it?
Yes.
And in physics, what does down mean?
Negative.
Negative. We can show it went down with a negative sign right here. So that's going to be a negative 5 or 8.52. Okay, one more variable that we know. What is acceleration?
Negative 9.
Negative 9.8 meters per second squared. Right? Okay. I promise if you can do that, the rest of these questions we're gonna solve are going to be easy. If you can draw a picture and label all the variables like we just did here. Okay? Now we need to pick an equation. What are we really looking for, guys? What do we need to find? Time final. So, we need to pick an equation with time in it. Can I pick equation number 3?
No.
No. Why?
It doesn't have time.
It doesn't have time. It wouldn't do us any good. Can I pick equation number 1? Now, to solve an equation, I need to have all the variables except for time. Do I have velocity final? I don't. Do I have time? No. So I don't have either of these. Can you solve an equation with 2 unknowns? No. So I cannot use number 1 either. See how we just eliminated that? Okay. What about equation number 2? Can I use it? Do I have displacement final?
Yes.
Yes. Do I have displacement initial? Yes. Do I have initial velocity?
Yes.
Yes. We don't have time, but we could solve for it. Do I have A? Yes. And I don't have time final. So there's only one unknown there, and that's time final. So can I solve it? Yes. So let's plug it into equation number 2. And by the way, this is kind of the go-to equation. If there's one equation to know and try first, it would be number 2 here. Okay, so let's plug them in. All I'm going to do is take this equation now and plug it in. What's displacement final? Negative 8.52. And yes, the signs matter. You got to have the correct sign. Is equal to, what's displacement initial? 0. Plus, what's velocity initial?
0.
0. So 0 times anything is going to be 0, right guys?
Yeah.
So can I just put a 0 in for that term?
Yes.
Yes. Plus 1/2. What is A?
Negative 9.8.
Negative 9.8. And what's time final? Well, we don't know it. I'm just going to keep it, T sub F. But what do we got to do to that?
Square it.
Square it. Don't forget to do that. Okay, now we have an equation with one unknown. Can we solve it?
Yes.
Yes, we can. I'm going to simplify it as much as we can here. Negative 8.52 is equal to, let's take 1/2 of negative 9.8. What is that? Isn't that a negative 4.9? And I've still got time final squared. Okay, so I've simplified it to that point. Didn't do anything yet. We haven't done anything crazy. Now, what would you do, guys, if we're trying to solve for time final? What would you do?
Divide by negative 4.
Good. We got to get time final by itself. Let's divide this side by a negative 4.9. But it's an equation. Whatever we do to this side, we got to do to this side. What's a negative 4.9 divided by a negative 4.9? Well, it's 1. You can cancel it out. Now let's rewrite this. Simplify it. So on the left side, we got a negative 8.52 divided by a negative 4.9. Are you guys getting this? So 1.7, let's just call it 74, is equal to time final squared. How do I get rid of that square?
Square root.
Square root. So if we square root time final squared, we're left with time final. But we've also got to square root the other side. So time final is equal to the square root of 1.74. And what do you guys get?
1.32.
Time final is equal to 1.32. And what's my units going to be?
Ton of seconds.
Seconds. Yeah, time is always measured in seconds. So please make sure you put the units as well. Circle it somewhere so that you can see where the answer is. So those shingles, if Luke dropped the shingles, they're going to be in the air for 1.32 seconds. Hey, can we do that, guys?
Yes.
We can. These aren't too bad. Let's go to practice problem number 20. Okay, it says Rex throws his mother's crystal vase vertically upward with an initial velocity of 26.2 meters per second. Probably not a good idea, right? Determine the height to which the vase will rise above its initial height. Choose one of the following equations to help you solve this problem. Okay, now first of all, is that vase in free fall? Yeah, I mean it's only acted upon by gravity, right? That's the only thing that's moving through the air. Okay, so choose one of the following equations to help you solve this problem. So again, we've got these three equations. But what's step number one, guys? Draw a picture. Please, draw a picture of it, okay? Here's Rex. He's chucking this vase. I don't know how to draw a vase, but there we go. Okay, he's going to chuck it up with an initial velocity of 26.2 meters per second. That's pretty good heave, isn't it? It says, determine the height to which the vase will rise. So we want the height. Okay, so there's our picture. We know it's going to go up. Okay, we want its highest point. Okay, so there we go. Now let's label all the variables that we know. Do we know velocity initial? Right when he hucks it. What's it going to go up? Didn't it say initial velocity of 26.2? 26.2, and it's going up, so is it going to be positive?
Yes.
Yes, so that's positive. Do I know displacement initial? That point at which he releases it, let's just call it 0. Okay? Because we really want to know how high it goes. Do I know time initial? Yeah, let's just call it 0 seconds. That's where it's starting. Okay? Do I know acceleration? What's it going to accelerate at? Negative 9.8 meters per second squared. Okay, now let's list all the things at the top at its max height. I didn't really leave myself enough space, so I'm going to do it over on this side. What's displacement final? We don't know. Okay, what's time final? We don't know. What is velocity final?
0.
Good. Good. I hope you guys see that. When you throw something up, how fast is it going at its apex, at the top of its path?
0.
It's going, yeah, just imagine throwing something up. At its max height, it's going 0, right? It's for an instant in time, its velocity is 0. So, velocity final there is 0. I hope that you guys can see that. Okay, now do I have all my variables? Do I have the picture drawn, and all the variables? Yes. So now let's pick an equation.
3.
What do I really want to know, though? Displacement final. So, can I choose equation number 1?
No.
No. It does not have displacement in it. Okay? You can't solve for it. Can I pick equation number 2?
No.
How come?
Because you don't know time final.
I don't know displacement final, and I don't know the time. Can I solve an equation with 2 unknowns?
No.
No. So that eliminates 2. Well, I must be able to use 3, but let's make sure. Do I know velocity final? Yes. Do I know velocity initial?
Yes.
Yes. Do I know A? Yes. Do I know displacement final?
No.
No. Do I know displacement initial? Yes. So there's just one unknown. Let's plug in our information into equation number 3 and see if we can solve for displacement final. Okay. What's velocity final, guys? 0. And you're going to square it, but 0 squared is 0, so that's easy. What's velocity initial? 26.2. And you got to square it. Plus 2 times A. Remember, it's a negative 9.8 for A. Times displacement final. We don't know it, so I'm going to keep it displacement final. And displacement initial is what? 0. Okay, so there's an equation with one unknown. Let's simplify. What's 0 squared? Well, it's 0. What's 26.2 squared? Are you guys getting this? 686.44 plus, what's 2 times negative 9.8? A negative 19.6 times, what's displacement final minus 0? Well, it's just displacement final. Okay. So if that kind of notation throws you off, let's rewrite it. 0 is equal to 686.44 minus 19.6 displacement final. Okay. Now what would you guys do? I don't like the negative part. Can we add 19.6 displacement final to each side? That's what I would do. So let's add 19.6 displacement final to both sides. Okay. Over here, it's going to cancel out. That's exactly why I did it. So let's rewrite it. So we've got 19.6 displacement final is equal to 686.44. Okay, now I'm solving for displacement final. How do I get it by itself? What would you guys do? Divide by 19.6, both sides, I agree. Over here, 19.6 divided by 19.6 is 1, so I can cancel it out. So displacement final is equal to, put it in your calculator, 686.44 divided by 19.6. What are you guys getting? Displacement final is equal to, are you guys getting 35.0 meters? And displacement will always be measured in meters, guys. So he threw that thing up pretty high, didn't he? 35 meters, imagine that. Hopefully he can catch it when it comes back down, right?
Well, even if you caught it, it would shatter.
Well, yeah, maybe. Okay, I got 2 more. Let's see if we can get them done. Practice problem number 21. If you're watching the video, it might be a good idea to pause the video, see if you guys can solve it, and then hit play when you have an answer and see if you got it right. Okay. All right, for us, we're going to work right along with it. So it says a baseball is popped straight into the air and has a hang time of 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. Hint, the time to rise to the peak is 1/2 the total hang time. That's an important point. This hint here is true of all free-falling objects. If I throw this pen up in the air and it takes 5 seconds to go up and down, at what time was it at its peak? Half of it, 2.5, right? Okay. Always remember that. If your hang time is 10 seconds, at what point will it be at its highest? At what time will it be at its highest point? 5 seconds. So always half, okay? That's kind of an important hint. Okay, so let's draw a picture. Okay, we've got this baseball player. He's got the bat. He hits the ball straight up. And to go straight up and then back down, so it goes up and then back down in 6.25 seconds. That was its hang time. Okay, what are we trying to solve for? Determine the height. So I always like to circle what it's asking for. We need height. Let's list the variables that we know. What's time initial, guys? 0. What's displacement initial? 0. What is velocity initial?
0.
Well, initially it's got to have some velocity to get up, right? So we don't know it. It didn't tell us. Okay. What's acceleration? Negative 9.8. That's always the same. Now let's go to the very top. Let's go to its apex. Let's go to right here and list the variables. Do I know displacement final? No, that's really what I'm trying to look for. Do I know velocity final?
0.
Good. It's going 0 at its apex. So always remember that. Remember, if it goes up, and it kind of at this point, there's a moment in time where its velocity is 0 at its highest point. Okay. Do I know time final?
Yes.
I do. What is time final?
3.125.
Good. If you take the hang time and divide it by 2, that will tell me the time at which it was at its highest point, 3.125 seconds. Okay. Now I've got a picture. I've listed the variables. Let's pick an equation. Which one do I really want, though, guys? Displacement final. Should I use equation number 1?
No.
No. What about equation number 2? I don't have displacement final. Do I have initial? Yes. Do I have velocity initial?
No.
No. So can I use equation number 2? Nope. What about equation number 3? Do I have velocity final? Yeah, it's going to be 0. Do I have velocity initial?
No.
Nope. So I don't have that one. Do I have A? Yeah. Do I have displacement final? No. So what do we do here, guys?
You find velocity initial first, and then look for displacement.
Okay. I need to somehow find velocity initial.
So
How could we do that?
Number 1.
Could we use equation number 1 to solve for velocity initial? Let's find out. Do we have velocity final?
Yes.
Yes, that's 0. We don't have velocity initial. Do I have A?
Yes.
Do I have T?
Yes.
Yes. So let's use equation number 1. Now that's not going to answer the question, but it will help us answer the question. Okay, what's velocity final? 0. Remember, at its highest point, it's going to be going 0. What's velocity initial?
Wait.
We don't know. I'm just going to keep it v sub i. Plus a negative 9.8. What's the time?
3.12.
3.125. Okay. Now let's simplify that. Okay, negative 9.8 times 3.125. So 0 is equal to velocity initial minus 30.625. Is that what you guys got?
Yes.
Okay, now how would you solve this one? Can't you just add 30.625 to each side? And so velocity initial is going to be equal to 30.625 meters per second. Okay, I'm not going to circle it, but I'll underline it because we need that. Now that we have velocity initial, what equation should we plug into to get displacement final?
3.
Could we plug into equation number 2?
Yeah.
Okay, let's do it. Let's plug into this one. What's displacement final, guys?
That's what we're looking for.
That's what we're looking for. We don't know it. Okay, I'm going to keep it d sub f. Is equal to displacement initial is what? 0. Plus, what's velocity initial? Well, we just solve for it. 30.625 times time final. What was time final?
125. Oh,
3.125 plus 1/2. A is negative 9.8. Always remember the negative there. Times time final squared times 3.125 squared. Always remember the square. Okay, now let's simplify. Displacement final is equal to, let's do 30.625 times 3.125. Are you guys getting 95.7
Yes.
for this term? Okay. And plus, and this is going to be a negative because there's a negative sign right here, so it's going to be minus . Are you guys getting 47.85 for this last term right here? Anyone else verify that?
Yes.
Yep. Okay. So then, displacement final, we just have to take 95.7, subtract 47.85. Are you guys getting 47.85? And what does displacement measure in what units? Meters, yeah, it's displacement is measured in meters. So how high did that ball go? Well, it went 47.85 meters high. Isn't that cool? Guys, you can just plug into these equations and figure that stuff out. I think that's pretty cool. Okay, I've got one more practice problem. Let's see if we can do it. Practice problem number 22. The observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. How fast will the penny be going before it hits the ground? Okay. Again, draw a picture. Okay, you're at this observation deck. You're dropping this penny to the ground. Okay, let's list the variables that we know. Do we know time initial? 0. It's always 0. Do I know velocity initial? It's dropping it, so it's 0. Do I know displacement initial? Yeah, let's call that point 0 at which he releases it. Okay, do I know A? Negative 9.8. Okay, now let's go down here right before it hits the ground. Do I know time final? No. Do I know velocity final? Nope. Do I know displacement final? I do. How high was that skyscraper? 370 meters. But I'm going to call this what? Negative 370. Why is it negative 370? Because it's going down. Okay. All right. Now, what is it asking us to find? The time. And also, it has two parts. How fast. So we need velocity final and time. Okay? So we need to figure out which equation we could use first. Okay, so let's look at this. Let's solve this problem here. And to determine the time required for the penny to free fall from the deck to the street below. So let's look at equation number 1. We don't have velocity final and we don't have time. So we can't use equation number 1. Let's see if we could use equation number 2. We have displacement final, displacement initial. We have velocity initial. We don't have time. And we don't have time. Okay, so we can use equation number 2 to solve for time final. Okay. Let's just see if we could use equation number 3 and solve for velocity final. So we don't have velocity final. We do have velocity initial. I have acceleration. We have displacement final and displacement initial. So maybe we could use equation number 3 to solve for velocity final. And then if we had velocity final, we could use equation number 1 to solve for time. So maybe that's the course I would take in this one. So let's try it. So velocity final squared is equal to velocity initial was 0 squared plus 2 times acceleration is negative 9.8 times displacement final is negative 370 minus displacement initial is 0, so I'm just going to not put minus 0 because that doesn't change it. Okay, so if we simplify this one, velocity final squared is equal to I'm getting positive 725 points. No. positive 7,252. Okay. Again, it's positive because you have negative times a negative. Now, to get rid of the square, we're going to have to square root both sides. So square root of 7,252. So velocity final is going to be equal to 85.2, and velocity is measured in meters per second. Okay, so that's how fast the penny will be going. Now, it also wanted to know how long this process will take for that penny to hit the street below. Now that we have velocity final, I think we can use equation number 1 because we have velocity final, we have velocity initial, we have acceleration, and we don't have time. So let's plug into equation number 1. So velocity final is 85.2, but it's going to be negative because it's going down. And that's going to be equal to velocity initial was 0. Acceleration is always negative 9.8. It's going down. And times time. We don't know. Okay. So let's simplify this. Negative 850 or 85.2 is equal to a negative 9.8 times t. Okay, so let's simplify, try to solve for t. You would have to divide by negative 9.8 both sides. Over here it cancels out. And time is equal to negative 85.2 divided by negative 9.8. A negative divided by negative is positive, so time is equal to 8.69 seconds. And so that penny will be in the air for 8.69 seconds. And when right before it hits, it's going to have a velocity of 85.2 meters per second. Anyway, I hope that helps. I hope that helps, guys, with these free fall problems. You now know enough to do a worksheet in the student workbook. So I'd like you to open up your books and flip to, it's called Free Fall Worksheet. And I promise if you go through those steps, draw a picture, label the variables, then pick an equation that will work, I think we can do these problems. So hopefully that helps.